Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we introduced the idea of a set and kind of opened up this topic of set theory. And in this video what we're going to do is we're just going to cover a brief video of some of the notation that we'll use throughout the course for some useful number systems or useful sets that you may have already seen within the calculus component or even at A level. So let me go to our first definition here, which is going to be the number systems that we're going to be using throughout the course. So the following notation is going to be used to define these sets of numbers or number systems. And the first set that we're going to look at is going to be called the natural numbers. So we denote it by this kind of n. And the natural numbers, as you might expect, are the numbers 1, 2, 3, going on forever and ever. We use this ... notation here that we adopted in the previous video to mean that we continue according to the previous prescribed pattern. So the next number would be 4, and then the next number 5, and so on. And the natural numbers are sometimes often referred to as well as the counting numbers for obvious reasons, that they count as they go along. Right? I count 1, 2, 3, going on, so on, so. Now from the natural numbers, I can construct the integers, which in other words is just all the natural numbers plus all the negative natural numbers and 0. So I write that down as this kind of Z symbol, and that now takes all the negative integers, all the positive integers, and the number 0. And we use this ... notation now on the left-hand side, which we haven't seen before, but is fairly obvious what we mean. That instead of, we now go from the prescribed pattern of -1, -2, going on that pattern, which would be then -3, -4, and going on forever and ever. And then on the other side, we go 0, 1, 2, 3, 4, and going on forever and ever. So that would be what our set of integers are. Now, the next step is to build effectively the fractions, which we call the rational numbers, out of the integers and the natural numbers. So how do we do that? Well, we denote it by this q here, and we have it as a over b, so it's kind of a fraction. But we have the condition that a now is an integer, and b is a natural number. The reason why we have this condition is we don't want the bottom to have the number 0 in, because we don't want to divide by 0, at least not in this course. And then the final set of numbers, which are the ones that you probably have worked with most in your life, are the real numbers. Now, the real numbers, we're going to say here, are effectively just the rational numbers and the numbers that are not rational. In other words, we say that those are the irrational numbers. So we combine together the rational numbers and the irrational numbers, and that constructs our real numbers. Now, notice here that the real numbers are a little different to the other three, because the other three we kind of constructed as we went along. The counting numbers or natural numbers emerged kind of naturally out of counting. The integers emerge out of kind of the natural numbers by adding negative and numbers and 0. The rational numbers emerged out of the natural numbers and the integers. But the real numbers, we kind of say, oh, well, we've got the rationals, but what are these other numbers, the irrationals? Seems a bit strange compared to the other number systems. Well, in fact, how you construct the real numbers from these other number systems is you can construct the reals from the rationals and considering infinite sequences of rational numbers. So effectively what you notice is that the rational numbers are incomplete. In other words, there's gaps in the rational numbers. There are numbers that are out there that are effectively solutions to equations that are not rational. For example, like the square root of 2. You may have already seen this in school. And how you can construct these numbers, these irrational numbers, is you realize that you can get infinitely close to the irrational numbers by taking effectively a sequence of rational numbers. And this is otherwise known as completion. So you take the rational numbers and you complete that number system, and that effectively gives you the real numbers. And you'll hopefully see this in the calculus component of the course. And what we say then is that the real numbers are in fact complete. In other words, that's kind of another way of saying that there's no gaps in the real numbers. If I point or if I put my finger at any point in the real number system, it will fall upon a number. Unlike the other number systems, where if I put my finger somewhere in the system, it will miss. There might be some gaps in there. So the next thing to consider is another type of special set that you may have seen in the previous part, which is known as the empty set. Now, the empty set, as you might expect, is simply the set that contains no elements, and we denote it by this 0 effectively with a line through. And unlike the other sets, actually the empty set is rather special. You might think it's rather boring because it's empty, but in fact the empty set is special in the sense that it's unique. It's the only set of its type that contains nothing, right? It contains no elements. In fact, the empty set is one of the key components to not only constructing the idea of sets or constructing axiomatic set theory, but it's also key to constructing the natural numbers. In fact, you construct the counting numbers out of sets of the empty set. So that's a way of constructing the natural numbers. And from the natural numbers, we built all the other number systems. But we're not going to go into that too much. And in the final thing, or the final definition we want to look at, is some special subsets of the real numbers that we need to consider, or that will appear a lot. And this is because the real numbers, as we said, are complete. So we can consider these kind of continuums of number sets in the real numbers, which are like some subsets. And we use these things as open, clopen, and closed sets. And we say an open set is effectively this open bracket AB, and we denote that by the set of numbers in the reals such that they're between the numbers A and B, but they can't take the values of A and B. So it's just this interval A to B, but the value, it can't take the values of A and B themselves. Then naturally that leads to this idea of a closed set of R, which is going to be denoted using these closed brackets. And that's exactly the same as the open set now, but apart from the fact that we can take values of, the values in this set can be actually A and B. So we can take both the kind of extreme points of this set. And finally, as you might expect, a clopen set, or sometimes called a half open set, is one that we just have a kind of closed bracket on one side and an open bracket on the other. In this case, we're taking a closed bracket on A and an open bracket on B. So that tells us that X can take the value of A, but it can't take the value of B, and it's in between A and B. So that is X is greater than or equal to A, but less than B. And similarly, if I flip it round, if I take the closed bracket on B and the open bracket on A, I have X is strictly less than or equal to B, but greater than A. So that's basically everything in this video. It's just a bunch of definitions for the number systems, the empty set, and open, clopen, and closed sets. And in the next video, what we're going to do is we're going to start actually studying this point here that I made about subsets. We're going to ask what it means to say that something is a subset of a larger set. So again, I always reiterate, please read the notes after watching this video, and also type with any questions that are on the module handbook that might be relevant to this video. So I'll see you in the next one.